Hello. Thank you all for coming. This is going to be a talk by my friend, the journalist and science writer, Anil. Please silence your phones. And on Google, we can have some copies of the book for you to take home if you're interested by what he has to say. Anil and I worked together as software engineers more than 20 years ago in Berkeley, and we've been in touch, but not nearly enough. And he has had such a exciting career that went to the edge of physics, one of his other books. And yes, please welcome Anil for his presenting his latest book that's just out.
Yeah, so thank you, Anu, for that introduction. Anu and I go back a long way. I was a software engineer before I became a journalist, and it's really a pleasure to be speaking here at Google. The last couple of times I came to speak were for my previous two books, which I really enjoyed the talks. The first one was called The Edge of Physics, and the second one was called The Man Who Wasn't There. And both of those books, I was able to sort of tell stories about people and places that I visited. This book is somewhat different. The protagonist of this book is a single experiment. It's an experiment with a 200-year-old history. This book is really the story of quantum mechanics told through the lens of one experiment and its modern variations. So it's a slightly different kind of book in the sense that it's hard to tell stories in the way that I could have done with the previous two books. So what I thought I'd do is I'll start by just reading a few pages, just 4 or 5 pages from the book, the opening 4 or 5 pages, just to give you an idea of how a writer might want to think about opening a book, which is actually quite nerdy at some fundamental level, because it really just gets into the details of this one experiment. But you still want to write it in a way that's appealing to almost anybody who wants to pick it up. And then I have a set of slides that I would like to go through just to tell you what this experiment is. Most of you would be very familiar with this experiment. It's called the double slit experiment. But it's amazing how much this particular experiment pervades quantum mechanics. So I want to run you through a few slides just to talk a little bit about what it tells us about the big conceptual issues in quantum mechanics. And then we can have a short Q&A. So if you don't mind, I'm going to start reading from the book. So this is the prologue. The story of nature taunting us. The office is simply the most uncluttered of any physicist office I've ever seen. There's a chair alongside a small table with nothing on it. No books, no papers, no lamp, no computer, nothing. A sofa graces the office. Large windows overlook a small lake, and the trees around which are bare, except for a few stragglers that are holding on to their fall foliage, defying the approaching winter in this part of Ontario, Canada. Lucien Hardy puts his laptop on the table, pointing out that he does most of his work in cafes and figures that all he needs in his office is a cafe-like small table to set down his laptop. There is the obligatory blackboard, taking up most of one wall of his office. It doesn't take long for Hardy to spring up and start chalking it up with diagrams and equations, something that most of the quantum physicists I meet seem inclined to do. We start talking about some esoteric aspect of quantum physics when he stops and says, "I started off the wrong way." To reset our discussion, he says, "Imagine you have a factory and they make bombs." He has my attention. He writes 2 names on the blackboard, Elitzur and Vaidman. He's talking about something called the Elitzur-Vaidman bomb puzzle. Named after 2 Israeli physicists, the puzzle exemplifies the counterintuitive nature of the quantum world in ways that non-physicists can appreciate. It confounds physicists too in no small measure. The problem goes something like this. There's a factory that makes bombs equipped with triggers. The triggers are so sensitive that a single particle, any particle, even a particle of light, can set them off. There's a big dilemma, however. The factory's assembly line is faulty. It's churning out both good bombs with triggers and bad bombs without triggers. Hardy writes them as, quote, good and bad, and quips about the quotation marks. Obviously, you may have a different moral perspective on it, he says. The task is to identify the good bombs. This means having to check whether the bombs have triggers. But examining each bomb isn't the correct strategy, because in order to do so, you would need to shine light on it, however faint, and that would cause a good bomb to explode. The only ones unexploded would be the duds without triggers. So how does one solve the problem? If it helps, we're allowed one concession. We can detonate some bombs as long as we're left with some good undetonated bombs. From our everyday experience of how the world works, this is an impossible problem to solve. But the quantum world, the world of very small things like molecules and atoms and electrons and protons and photons, behaves in bizarre ways. The physics that governs the behavior of this microscopic world is called quantum physics or quantum mechanics. And we can use quantum physics to find good bombs without setting them off. Even with a simple setup, it's possible to salvage about half the good bombs. It involves using a modern variation of a 200-year-old experiment. Called the double-slit experiment, it was first done in the early 1800s to challenge Isaac Newton's ideas about the nature of light. The experiment took center stage again in the early 20th century when two of the founders of quantum physics, Albert Einstein and Niels Bohr, grappled with his revelations about the nature of reality. In the 1960s, Richard Feynman extolled its virtues, saying that the double-slit experiment contained all of the mysteries of the quantum world. A simpler and more elegant experiment would be hard to find, the workings of which a high school student can grasp, yet profound enough in its implications to bewilder brains like Einstein's and Bohr's, a confusion that continues to this day. This is the story of quantum mechanics from the perspective of one classic experiment and its subtle, sophisticated variations, including one that, as we'll see, solves the Elitzur Vaidman bomb puzzle. Whether these variations are carried out as thought experiments by luminous minds or painstakingly performed in the basement labs of physics departments, it's the story of nature taunting us. Catch me if you can. So I will read a couple more pages from the opening chapter. And this chapter actually begins by talking about a lecture that Richard Feynman gave, which is one of the most extraordinary lectures you can see. It was given in 1964. And it became a very nice way to actually open the chapter, just to talk about what he was saying. So chapter 1, the case of the experiment with two holes. Richard Feynman explains the central mystery. Richard Feynman was still a year away from winning his Nobel Prize and 2 decades away from publishing an endearing autobiographical book that introduced him to non-physicists as a straight-talking scientist interested in everything from cracking safes to playing drums. But in November 1964, to students at Cornell University in Ithaca, New York, he was already a star, and they received him as such. Feynman came to deliver a series of lectures. Strains of Far Above Cayuga's Waters rang out from the Cornell chimes. The provost introduced Feynman as an instructor and physicist par excellence, but also, of course, as an accomplished bongo drummer. Feynman strode onto the stage to the kind of applause reserved for performing artists and opened his lecture with this observation. It's odd, but in the infrequent occasions when I have been called upon in a formal place to play the bongo drums, the introducer never seems to find it necessary to mention that I also do theoretical physics. By his 6th lecture, Feynman dispensed with any preamble, even a token hello, to the clapping students, and jumped straight into how our intuition, which is suited to dealing with everyday things that we can see and hear and touch, fails when it comes to understanding nature at very small scales. And often, he said, it's experiments that challenge our intuitive view of the world. Then we see unexpected things, said Feynman. We see things that are very far from what we could have imagined. And so our imagination is stretched to the utmost, he said, not as in fiction to imagine things which aren't really there, but our imagination is stretched to the utmost just to comprehend those things which are there. And it's this kind of situation that I want to talk about, he said. The lecture was about quantum mechanics, the physics of very small things. In particular, it was about the nature of light and subatomic bits of matter such as electrons. In other words, it was about the nature of reality. Do light and electrons show wave-like behavior like water does, or do they act like particles like grains of sand do? Turns out that saying yes or no would be both correct and incorrect. Any attempt to visualize the behavior of the microscopic subatomic entities makes a mockery of our intuition. They behave in their own inimitable way, said Feynman, which technically could be called the quantum mechanical way. They behave in a way that is nothing like you've ever seen before. Your experience with things that you have seen before is inadequate, is incomplete. The behavior of things on a very tiny scale is simply different, he said. They do not behave just like particles, they do not behave just like waves. But at least light and electrons behave in exactly the same way, said Feynman, that is, they're both screwy. Feynman cautioned the audience that the lecture was going to be difficult because it would challenge their wildly held views about how nature works. But the difficulty really is psychological, he said, and exists in the perpetual torment that results from your saying to yourself, but how can it be like that? Which really is a reflection of an uncontrolled, but I say utterly vain desire to see it in terms of some analogy with something familiar. I will not describe it in terms of an analogy with something familiar, he said, I'll simply describe it. And so, to make his point over the course of an hour of spellbinding oratory, Feynman focused on the one experiment which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and mysteries and peculiarities of nature. It was the double-slit experiment. It's difficult to imagine a simpler experiment, or as we'll discover over the course of this book, one more confounding. We start with the source of light. Place in front of the source a sheet of opaque material with two narrow, closely spaced slits or openings. This creates two paths for the light to go through. On the other side of the opaque sheet is a screen. What would you expect to see on the screen? So that's how the book begins. And I think for the rest of the talk, I just want to run through the experiment and point out some of the big conceptual issues in quantum mechanics that this one simple experiment addresses. So this is the experiment that was first done 200 years ago. There's a source of light, it's shining at an opaque sheet with two slits cut into it, and you're asked the question, what would you expect to see on the other side? Your intuition pretty much says, oh, I should just see two strips of light on the other side. Actually, the answer really depends on what you think is the nature of light. And in the 17th century, thanks to Isaac Newton, our ideas about the nature of light were really due to his corpuscular theory of light. Newton said that light is made of corpuscles or particles. So if light is made of particles, and if you're streaming a beam of particles at these two slits, then that you expect a certain result to come out of this experiment. So, and instead of thinking about light, let's just for a moment just think about, say, particles that we understand, particles of sand, for instance. So this might be a sand blaster just blasting sand at these two slits. So if, say, the right slit is closed, right, what do you expect? You expect to see the sand go through the left slit and hit the screen, right behind the open slit. The same thing if the left slit is closed. You expect to see the sand go through the other slit, the closed left slit is obstructing the sand. So basically, you're seeing the particles hit the screen right behind the open slit. And if you were to now open both slits, our intuition tells us that this is what should happen, right? You should basically see two strips of particles hitting the screen on the back of the opaque screen. This is not what happened. When the experiment was first done in the early 1800s by an English physicist called Thomas Young, he saw something completely different. He saw this. He saw bands of light and dark appearing on the other side of the two slits. So here, think of the screen as a photographic plate. So the dark bands are where most of the light is hitting. And so it's a negative. So the dark bands are where the light is hitting. And you can see that there are alternating dark and light bands. So there's light, there's no light, there's light, no light, right? This can only be explained if you think of light behaving like a wave. So the wave hits the two slits, and then from each slit, two new sets of waves start coming out. They spread. Eventually, they will interfere with each other. And the places where these two sets of waves interfere constructively, meaning the crests of one wave line up with the crest of the other, you get constructive interference. And when the crest and the trough line up, you get destructive interference. So essentially you get this interference pattern. This is absolutely characteristic of waves. You can see this anywhere you see waves, for instance, with water waves on a lake or in the ocean. Now, this idea that light behaves like a wave kind of held through pretty much through the the 1800s, and then along came quantum mechanics. Early 1900s, Einstein was the first to point out that light, there are certain situations in certain phenomena in nature, particularly the photoelectric effect, which is what he was talking about at the time, can only be explained if you think of light as being made of particles. So quantum mechanics says that all energy is quantized, light is a form of energy, and so light is made of individual, indivisible quanta and these quanta can be called particles of light. Now, this same experiment becomes incredibly confounding. So if you go back to this, now imagine that your source here is beaming, say, red laser light, so light of one frequency. And we now know from quantum mechanics that light is made of particles. So this is beaming out individual particles. Now, imagine also that you can turn down the intensity of this laser light to the point that only one particle of light is coming out at a time. Just one at a time, maybe one every 5 seconds, one every 10 seconds, doesn't matter. But just one particle is going through the apparatus at any given time. And now what do you expect? Now your intuition pretty much says that it should behave like particles of sand, because you know classically you're thinking it should go through one slit or the other and it should end up on the photographic plate right behind the open slits. And any guess as to what happens? This is quantum mechanics. Obviously that's not going to happen. You get exactly the same result, except that this is what starts building up. If there is a photographic plate on the other side of the slits, and if you're sending one particle at a time, in the beginning it seems like the particles are randomly going to certain locations on the plate, but over time, as the pattern develops, you see that the same interference pattern develops, right? This is again indicative of some interference that's going on, except, and this is something really important to appreciate, you're creating a particle and you're detecting a single particle. And nothing, when a single particle is going through the double slit apparatus, it is not interacting with any other particle. There's just one particle in the apparatus at any given time. So yet an interference pattern is emerging. So what is interfering with what, right? So this becomes a really important question to ask, and ends up being the central question in trying to understand some of the conceptual issues with quantum mechanics. So if you're now shooting individual photons of, say, red light of a given frequency at this particular double slit, then you get this interference pattern at the back, which is exactly the same that you saw when there was lots of light going through the double slit. So the question is, what is it that is interfering? So mathematically, there is an explanation. So mathematically, each photon or each particle of light is represented by what physicists call a wave function. It's a mathematical abstraction. This wave function is a function. It's a function which tells you what its value is at some point in space and time. And this function evolves according to something called the Schrödinger equation. So there is an equation that tells you how this wave function changes with time. And mathematically, the way you model this system is you let this wave function propagate towards the two slits. It hits the two slits. It acts exactly like a wave. It goes through both slits. On the other side, you have two sets of waves coming out, and they interfere, and you get an interference pattern. But you're getting an interference pattern of a mathematical abstraction, right? What is this wave function? What has this wave function got to do with a single particle? And that is really the central issue that this particular experiment starts addressing. So we can start asking, what is it that's interfering? There is a wave function that's going through the two slits and interfering and creating an interference pattern on the other side, but the wave function is a mathematical abstraction. For any system of more than two particles, this wave function doesn't even exist in normal three-dimensional space. It exists in a mathematical space called configuration space. It can have a large number of dimensions depending upon what your number of particles are. So what is actually going through the two slits? And it's very, very unclear as to what is happening here. So the wave function goes through the two slits, a mathematical abstraction. You can calculate what the interference pattern is on the other side. And then the interference pattern tells you basically the value of the wave function at various points in space. And you can then ask, what is the value representing? It turns out it's not really telling you where the photon is or where the particle of light is. The value of the wave function at any point in space is only giving you the probability of being able to find the photon there if you look for it. So it turns out that the interference pattern created by the wave functions, there are many, many regions where there is a non-zero probability for the photon to end up in. So you have a single photon that is going through the two slits. It's being represented by a wave function which essentially goes through the two slits, interferes on the other side, and on the other side you have these various regions of constructive interference which all have non-zero probability for the photon to end up in. For any given photon, when you send it through the two slits, there is no way to tell exactly where it will end up. So it's non-deterministic, right? You've created a single photon. It somehow has gone through the two slits. On the other side, it's going to end up in one of many locations which have a non-zero probability. So this wave function is essentially a way to calculate what is the probability of finding a photon in some location on the other side. And it turns out that when you do a measurement, in this case the photon interacting with your photographic plate is the measurement, that measurement somehow collapses that wave function which until the measurement happened gave you probabilities of the photon as possibly being in, gave you probabilities of finding the photon in many different places. But the moment you do a measurement, when the wave function interacts with the photographic plate, the wave function collapses. The photon is found in one place and not in any of the other places that it could have been. So this act of measurement, kind of collapsing the wave function, is a huge issue in quantum mechanics, because quantum mechanics basically says that it's the measurement that is causing the collapse of the wave function. But it doesn't actually define what a measurement is. Standard quantum mechanics just divides up the world into quantum systems that are being measured and apparatuses that are doing the measuring, but there's no distinction, mathematically speaking, as to what constitutes a quantum system and what constitutes a measuring classical apparatus. There's also another mystery that this experiment highlights. Now, if you try to figure out which slit the photon is going through, like your intuition is telling you, no, come on, it's a single photon, it has to go through one slit or the other, and say you set up a system where you can tell which slit the photon is going through without destroying the photon, then the interference pattern disappears. So if you try to look to see which slit the photon went through, the interference pattern disappears. If you don't look, there is an interference pattern, right? So all of these things start leading to questions about what is really happening at that very, very basic level of reality. It's very clear intuitively that the photon can't possibly be going through both slits at once. Right? I mean, you've created a single photon, you've detected a single photon, all your classical intuition is telling you surely it's not going through both slits at once. But something is going through both slits at once because you are getting an interference pattern. So is the wave function going through both slits at once? But then what is the wave function? The wave function is a mathematical abstraction. We have no idea what that is. It exists in some abstract configuration space and interferes, but that's just mathematics. We don't know if that is real. So if that's not real, then again the question comes back, then what is going through both slits? So this circular argument keeps going. This idea of the wave function being real or not real, whether it is actually representing something that is happening in reality, in the sense that it represents something actual about reality, it's part of the ontology of the world, or is it does it just represent our knowledge about what's happening? So is the wave function ontic or ontological, or is it epistemic? These questions are yet undecided in quantum mechanics. We really don't know the status of the wave function as to what that really is, right? So these kinds of, you can see that just this one simple experiment, the moment you try to understand what's happening, it completely explores this whole business of what actually is the nature of reality. I just want to run you through one very a simple version, a modern version of this double-slit experiment. It's called a Mach-Zehnder Interferometer. And this will lead us to trying to answer the question about how do you detect that bomb which had live triggers versus a bomb that had duds, right? So this is the beginning of what's called a Mach-Zehnder Interferometer. A photon or light hits this thing called a beam splitter. A beam splitter is simply a half-silvered mirror. Any window pane actually works. Like you can see, if you look at a window pane, some of the light is getting transmitted and some of it is getting reflected. So if you imagine a laboratory grade beam splitter, it's reflecting exactly half the light and transmitting exactly half the light. Half the energy of the light that is incident on this beam splitter goes one way, half of it goes the other way. And that kind of works when you're thinking about a lot of light. If you just take a flashlight and shine it at the beam splitter and half is reflected, half is transmitted, that makes sense. But now, remember, it's quantum mechanics, so you're allowed to talk about single particles of light. So now what happens if a single particle of light is incident on this beam splitter? Now, we know from quantum mechanics that the single particle of light cannot be divided any further. It is the quantum of energy. It is the smallest quantum of energy. So turns out, quantum mechanics says that the photon, in this case, will be reflected with 50% probability and transmitted with 50% probability when it hits a beam splitter. So basically, it's either going to be reflected or transmitted. And for any given photon, you can't tell what it will do. But if you send thousands and thousands, on average, half will go one way, half will go the other way, right? So we can now put detectors at the end of these paths, and these detectors are going to click half the time for the photon being reflected, half the time for the photons being transmitted, right? So we can now sort of make this configuration a little bit bigger. All that this figure has done is it has turned the paths of the two beams at right angles. It's still the same. A photon goes into the first beam splitter and then ends up either in detector D1 or ends up in detector D2. So if you were to send 10,000 photons into this beam splitter one by one by one, on average, 5,000 are going to be reflected, 5,000 are going to be transmitted. It's half the time D1 will click, half the time D2 will click, right? This is you can do this in the lab. This will happen all the time. Here's what happens when you complete the Mach-Zehnder interferometer. Something very, very intriguing happens. If you put another beam splitter exactly at the place where the two beams cross, right? Now, if D1 clicks, right? If you look at the previous figure, right? If D1 clicks here, if the detector D1 clicks, it's very clear that the photon took the reflected path. If D2 clicks, it's very clear that the photon took the transmitted path. But in the full interferometer, now the photon is reflected or transmitted by the first beam splitter, and it's also reflected and transmitted by the second beam splitter. Now, so if now D1 clicks, can you tell which path it took? Any thoughts? So there's no way to tell, right? I mean, if D1 clicks, the photon could have been reflected first and transmitted next, or it could have been transmitted first and reflected next, right? And now, if you send, say, 5,000 photons into this one by one, what do you expect if you do the numbers? Previously, remember, we said half will, if we send 5,000 into it, 2,500 will go to D1, 2,500 will go to D2 on average. We can't tell what any single photon will do, but on average. Now, what about this now?
Same. Yeah. Where else would they go?
Where else would they go, right? Your class, but this is quantum mechanics. This is a loaded question already, right? So, who said all of it will go to D1? Yes. So, this is the weird part. All of them will go to D1. And this very, very simple device illustrates just how funky quantum mechanics is, right? What's happening here, if you try to model mathematically what's happening here, the wave function of the photon, remember, some mathematical abstraction, which we don't know whether it's real or not, enters the first beam splitter. It now, part of it is going to be transmitted, part of it is going to be reflected, and it's going to continue on those two paths. And then at the second beam splitter, each component, the reflected component is again going to be reflected and transmitted. The transmitted component is going to be again reflected and transmitted, right? So if you now look at D1, D1 is going to be the combination in terms of the wave function, we're not thinking of the photon right now. We have to explain. So if you did this experimentally, if you just did this in the lab, all of the photons are going to go to D1. None will go to D2. As long as the path between the two beam splitters is exactly the same, all of them will go to D1, none will go to D2. And that's a really counterintuitive result that you need to explain. The mathematics explains it, right? So basically now you have to think in terms of the wave function. The wave function has split into two at the first beam splitter and then split into two again. Each component splits into two again. And then on the way to D1, there are two components of the wave function that are recombining. And on the way to D2, the two components are recombining. But it turns out that when you're going towards D1, the two components of the wave function, one which has been reflected and then transmitted, and the other which has been transmitted and then reflected, remember we're talking of waves, even though in mathematical space, these waves are in phase because they have endured the same amount of reflection and transmission, so they're actually in phase. So these two waves mathematically are, they are in phase and they constructively interfere. Whereas the waves that are going towards D2 has endured two reflections and two transmissions. So one component is lagging the other in phase by 180 degrees. The crests of one wave are lining up with the trough. That's destructive interference. So in that mathematical configuration space, the wave functions have interfered so that all of the stuff is going to D1 and none is going to D2. But remember, this is happening in abstract mathematical space. But this is representing the photon. So the photon always goes to D1. None will go to D2. And you can mess with these numbers by changing the lengths of the paths between the two beam splitters. But for now, if you think of them as equal, then D1 represents constructive interference, D2 represents destructive interference. No photon will go to D2, right? This does not make classical logical sense, but that's how the quantum world works. And you can only explain this if you're thinking in terms of the wave function and what's happening to the wave function, right? But the questions remain. What is the status of the wave function? Is it real, right? So if you, for instance, now put a block in one of these arms, what do you think will happen? Now, let's say we send 5,000 photons into the first beam splitter, but there's a block in one of them, one of the arms. What do you think might happen? Sorry?
Now it's happening.
Half enough, but what happens to the numbers? So we send 5,000 into the... So it turns out that the block will cut down the number of photons by half. But now, the wave function that is, so it's cutting down the wave function component that's going along one path. So nothing is going to progress along that path. The wave function that goes along the other path is now hitting the second beam splitter, but now there's no interference because there's nothing coming from the other side. So now it's just acting like before. Half of it goes one way, half of it goes the other way. So if you send 5,000, you're right, half will go to D1, half will go to D2, but half of 5,000. So 2,500 are blocked. The other 2,500 will hit the second beam splitter and then go half one way and half other way. This is now showing you that there's no interference. Putting that block is analogous to trying to see which way the photon is going. Right? In the double slit, if you blocked one of the slits, this is analogous to that. You're basically saying, I'm blocking one of the slits. I know now that the photon has to go through the other slit. Well, it does go through the other slit, and there's no interference. In this case, it becomes a very clear demonstration of the lack of interference when you block one slit. You open both slits, suddenly all the photons will go to D1. None of them will go to D2. Right? So this is showing you interference. Or rather, this is showing you the photon's particle-like behavior. It's acting like a particle. There's no interference. But the moment you remove that block, the moment you don't try to see which path the photon is taking, the system seems to behave like a wave and you get interference. So now I want to sort of talk about how this simple thing can help you solve the Elitzur-Vaidman bomb puzzle. So let me just tell you about the bomb puzzle again. What was the question? The question is, there's a factory that's making bombs, and these bombs have triggers that are extremely sensitive. So sensitive that even a single particle of light falling on it will detonate the bomb. The problem is that the factory is also producing duds, bombs without triggers, right? So your task is to figure out which bombs have sensitive functioning triggers and which are the duds. Now, in our classical way of thinking about this problem, if you were to look at the bomb to see if it has a trigger, it'll explode because looking involves shining light or something, you'll have to use some energy to look at it. And so, even a single photon will detonate the bomb. So there's no way classically, in our classical way of thinking, no way to solve this problem. But you can solve this problem. You can find out, you can distinguish the duds from the live bombs using this Mach-Zehnder Interferometer. You're allowed to detonate some bombs. So so what happens now? Say I have placed this bomb. Let's assume that all of this is being done in a dark room with robots and you're not worried about blowing up the bombs because of handling them. So let's assume that we can place the bomb right next to one path. And this one doesn't have a trigger. And now you start sending in photons to this, through this apparatus, to this interferometer. What do you expect? So 10,000 photons are going in. What do you expect? Where would the photons go? There's no difference between the previous, there's no difference between this and this because the bomb is just sitting there and it has no trigger, there's no obstruction, right? So this should just behave like a regular Mach-Zehnder interferometer. All of the photons should end up at D1. None should go to D2, right? So you really can't tell anything at this point. So let's say you did, you're trying to do this in a statistical sense. You say, I'm going to send 1 million photons into this, which you can do in labs these days very quickly. All of them will go to D1. None will go to D2. That's a very, very good indication that you have a dud next to your interferometer. Now, if you have a live bomb, right? Live meaning a trigger that will actually, it's placed so that it obstructs the photon path. Now what happens? Now you start sending in one photon at a time. Yeah, so this trigger now is like the block that we put earlier, right? Remember there was we had this setup where if we put a block, that block is going to obstruct half the photons. So this trigger now is like that block. Half the time the photons are going to hit this block, and half the time the bomb is going to detonate. So it will blow the bomb will blow up, so will the Mach-Zehnder interferometer. You'll have to rebuild it. Assume we can do all that. This is a thought experiment, so you can do all this, right? So half the time the whole setup will blow up. The other half of the time is the interesting part. The other half of the time the wave function is going through the other side, right? It's going through the other side, it hits the second beam splitter, and then what happens? Yes, so in this case, half the photons will end up at D2, right? So if you send 5,000 photons in, 2,500 of them on average will blow up the whole thing. The other 2,500 will get split up at the second beam splitter, and half of them will go to D2 and half of them will go to D1. If they go to D1, it's kind of inconclusive because D1 was happening previously also. But if any photon ends up at D2, that's a sign that there's a live bomb in the other path. But here's the interesting thing. You haven't interacted with the live bomb. Because if you had interacted with the live bomb, it would have blown up. No, but if it goes to D2, you know there's a live bomb. You can just pick that up and say, okay, this is what we're going to ship now, right?
Loading half the bombs and a quarter of them, you are sure.
Yeah, you can work out the probability. So this is the bare minimum, and you can fine-tune this experiment to improve that probability, right? But the idea here is something very, very profound, that quantum mechanics has allowed you to detect the presence of something without interacting with it. These are called interaction-free measurements. It does not happen in classical physics. You cannot measure something without interacting with it. Here we have physically interact. Well, physically is a different term. Something has interacted with the bomb. The photon hasn't, because otherwise the bomb would have exploded, right? But something interacted with the bomb, and we got information about the bomb without actually blowing it up. So this is an interaction-free measurement. This makes the case for the reality of the wave function, as if the wave function is probably the wave function that is sensing the bomb, right? This argument can go round and round and round. Yeah.
So that makes me think of the Heisenberg uncertainty principle.
Right.
And I can't remember from high school physics. Is that related to Newtonian physics or to quantum?
Heisenberg uncertainty principle very much. We'll come back to questions. So why don't we just wait for the question? I'll just finish up and then we'll come back. In fact, I just talk about that principle. So yeah, I mean this is an example of how this two slit. This is a very special case of the double slit experiment. This is the experiment that is done in labs on optical benches. It's very, very easy to configure and work with. And much of when physicists say that they're doing a double slit experiment these days, they're more often than not building a Mach-Zehnder interferometer and working with it. And there are variations of this in many forms. And it's amazing how this one simple experiment allows you to understand some of the very, very basic issues in quantum mechanics, like superposition. So superposition is this idea that we just talked about, that the photon can end up being in two paths at once. It doesn't make any sense. So there's a mathematical mathematical way of representing it. The way of talking about it is to say that the photon is in a superposition of taking both paths. It's not the same as saying the photon is actually taking both paths. It's just a way of saying that the quantum states are such that it behaves as if it is taking both paths. So it's the wave function that's taking both paths, but we don't know what the ontological status of the wave function is. So it's not the same as saying the photon is taking both paths. The uncertainty principle, right? These experiments allow you to talk about the uncertainty principle, which is the simple idea that there are certain parameters in quantum mechanics, in particular the position and momentum of a particle. You cannot measure both sort of accurately. If you measure one very accurately, you mess up the other one. So the more precisely you measure the position of a particle, the more uncertain the momentum, and vice versa. So that's the uncertainty principle. There's complementarity, or wave-particle duality. Complementarity being the idea that nature has two faces, the wave nature and particle nature. And you can only observe one or the other, and what you observe depends on the apparatus that you've built. So we saw that there were different configurations of that interferometer that you can build, which will either show you the particle nature or the wave nature, but you can't see both at the same time. Determinism versus non-determinism. Classical physics is deterministic. So, if you throw a ball and you know all the forces that are acting on it, you can predict exactly where it will go and the trajectory of the ball. Whereas here, when you're talking of a photon going through the double slit, you can only talk in terms of probabilities. You can only assign probabilities to where it will end up. There is no clear trajectory that you can map out that the photon takes. And basically this whole system is non-deterministic, and you can talk about determinism versus non-determinism in the context of the double slit experiment. The biggest problem really is this thing called the collapse of the wave function. Remember, the wave function goes through both slits, interferes, and on the other side you get this wavy thing that tells you mathematically what are the chances of finding the photon here versus here versus here. So, and if you did a measurement, it'll end up in one of those places. Until you did a measurement, the probabilities existed in this wave function, but the moment you do the measurement, the wave function collapses and peaks at one point. The probabilities go to zero everywhere, and it becomes one at the point where it's measured or where it's found. So, and there is nothing in quantum mechanics that tells you what this collapse really is. It's a postulate. It's an axiom in quantum mechanics that says when you do a measurement, the wave function collapses. We don't know what the wave function really is in terms of its reality. We don't know what the actual process of collapse is. And this thing is called the measurement problem. The idea that measurement causes collapse without being able to define what a measurement really is the cause of many, many conceptual problems within quantum mechanics. And a lot of the alternatives to standard quantum mechanics that you hear about are alternatives that are trying to solve the measurement problem. There's realism versus non-realism. Realism being this idea that there is an objective reality that exists independent of observation, that you don't need to be observing in order to know that there is a reality out there. Quantum mechanics, at least the standard way of thinking about quantum mechanics, questions that. The photon, in this case, doesn't have a reality until you observe it, because there is nothing in the mathematics that captures the trajectory of the photon from the source to the detector. There is, you cannot calculate the trajectory. It could have 5 different trajectories or any number of trajectories, so there's no way to tell. The only reality ascribed to the photon is at the point of creation and at the point of observation, right? So in one way of thinking about standard quantum mechanics, it actually denies reality until observation. So it is an observer-dependent theoretical framework. I mean, there are lots of issues with this. People debate this endlessly over and over again as to is that what it's really saying. But one way of interpreting standard quantum mechanics is to say that it's anti-realist. Then the questions about the wave function, which I just told you about, is it really something that exists, or is it representative of something that actually exists, or is it just our knowledge, half-baked knowledge about what's happening, right? Is it epistemic or is it ontic? I haven't even touched upon the other big issue in quantum mechanics, but the double slit experiment allows you to talk about that also, which is to do with entanglement or non-locality. The idea that if there are two quantum systems that are that have somehow interacted at some point, once they've interacted, they are now represented by the same wave function, and this wave function starts spreading, which means that maybe the particles are going apart, and if you do a measurement on one particle, you can instantly influence the state of the other particle, even if these things are kilometers apart. And that cuts against the idea of locality, which is the bedrock of relativity, which is the idea that what you do in one region of space-time cannot influence something else in another region of space-time any faster than the speed of light. Quantum mechanics apparently suggests that there is instantaneous influence. Action in one region can instantly influence the state of some other system and faster than the speed of light. So again, there are debates about whether that's really what it's saying, but there is enough proof that the underlying quantum reality is indeed non-local. Right? And the double slit and its variations, I just showed you one, the Mach-Zehnder Interferometer. There are many, many experiments that have been done that play on this principle. There's the Wheeler's delayed choice experiment. I don't think we have time to go through any. I just name them, and when you see them, you'll realize, when you see them in literature elsewhere, you'll realize that these are all variations of the double slit. The quantum eraser experiment, delayed choice quantum eraser, interaction-free measurements we just talked about. There are experiments that have actually tried to measure particle trajectories. I actually told you just now that you can't talk about trajectories in standard quantum mechanics, but there are other interpretations, other quantum formalisms that allow you to talk of trajectories, and there are ways in which you can measure them, and they're very controversial, but nonetheless you can do double slit experiments where you can map these trajectories. You can probe the divide between the quantum and the classical. Is the world quantum all the way through, or is there some divide where the quantum world gives way to the classical world? We don't know the answer to that yet. And there are a whole range of other things you can do that probe sort of conceptual issues in quantum mechanics, all using the double slit experiment. And my entire book is basically an exploration of how this double slit experiment has been used for all these purposes. And I talk about five interpretations. The Copenhagen interpretation, which is the standard quantum mechanics interpreted by the people who started it in Copenhagen, Niels Bohr, Werner Heisenberg, and a whole bunch of other people, Wolfgang Pauli. All these people were involved in an interpretation which is now called the Copenhagen interpretation. There's the de Broglie-Bohm interpretation, which is a very different view of the quantum world, which basically says the quantum world is both a wave and a particle. I don't think we have time to go into the details. There are collapse theories. So I talked about how the collapse happens because of measurement, and it puts observers at the center of everything. But there are theories which remove the observer. They basically cause collapse stochastically and then lead to the same predictions. And then there are people who take the wave function really seriously. They basically say that the wave function splits and never collapses, and each splitting wave function is giving rise to a different world. So essentially every time a photon goes through a beam splitter and goes left and goes right, you have created two universes. One universe in which the photon went left, one universe in which it went right, and so on. And then there's something called quantum Bayesianism, which is actually quite a complicated one to discuss easily. But anyway, these are the interpretations I deal with in the book. So yeah, I think I'll stop here and take questions. I hope that was informative. Thank you.
Much of what you spoke about, I think the kind of questions that were raised were probably around even probably say back in the 50s or 60s.
Yeah.
What has happened since then?
Good question. So since the mid 30s, late 1920s and early 1930s was when the standard formulation of quantum mechanics got formulated. So people like mainly due to von Neumann, Paul Dirac and others, so the standard quantum mechanics that exists is basically due to them, that by mid-30s was pretty much cast in stone. And then, but these conceptual issues, like you say, have been around. I mean, they were around even before 1950s. Einstein was arguing against these things throughout his career in quantum mechanics. Remember, he's one of the founders of quantum mechanics. Even though people don't, people ascribe to him, his greatest achievements are usually thought of as, the theories of relativity. He is one of the founders of quantum mechanics, and he had serious issues with these sort of questions that were raised just now. They haven't been solved. So the issues remain. The amazing thing about standard quantum mechanics is it is extremely successful. These probabilistic predictions, this mathematical framework that is used to make probabilistic predictions is the most successful physical theory we have. I mean, everything, like, all of the stuff that is happening right now with the electronics is happening because that theory works, right? But nonetheless, it raises fundamental questions about the nature of reality. We don't know. And so 1950 was the beginning of David Bohm's ideas. 1951 was when he came up with his Bohmian mechanics. But that has a precursor. It goes back to de Broglie in 1927. So the theory now is called de Broglie-Bohm, where you have a particle which is being guided by a wave, and the wave is real in Bohmian mechanics, except that, again, it doesn't move in 3D space, it moves in this mathematical configuration space. But in Bohmian mechanics, it is ascribed reality. It is part of the ontology of the universe, right? And somewhere in the 1980s, collapse theories came about. So this idea that, the wave function can collapse spontaneously, stochastically, without observers, without measurement. Right, so and then there's Penrose, Roger Penrose's ideas, which I didn't touch upon. It's not really mainstream, but he has some very interesting ideas about why gravity needs to be brought into the mix. So when you have two masses in superposition of being here and here, his argument is that these two masses will curve space-time differently, and then the two curvatures of space-time will also be in superposition of being, in two different curvatures, and that's unstable. And he figures out a reason, he admits himself that it's kind of rough calculations, but this instability of the two configurations of space-time will lead to a spontaneous collapse, right? And of course, small particles will take forever to collapse, whereas something larger, like a cat, will collapse immediately to either one or the other. Then there's quantum Bayesianism, which is very recent, last 10, 15 years. So, yeah, so it's happening. The point is that these issues are not resolved because all of these formulations or interpretations make exactly the same predictions. They have to make the same predictions in order to tally with experiments, right? So right now, experimentally, you cannot distinguish between these formulations. So Bohmian mechanics and standard quantum mechanics make exactly the same predictions, but they have a very different view of what the underlying reality is. Yeah. Anyone else?
Yeah, I guess following up on that, are any of these interpretations like testable, or are they always just going to be pure guesses? Like, I mean,
at this point, well, they're not guesses, right? They are mathematical. They're trying to. So Bohmian mechanics, for instance, the underlying reality is considered to be particles that are being guided by waves. These waves are considered real, except the waves move in configuration space, and it's kind of the mathematics is formulated to make exactly the same predictions as standard quantum mechanics, because otherwise it wouldn't be a valid theory. So right now there's no way to distinguish between standard quantum mechanics and Bohmian mechanics. Standard quantum mechanics has the other advantage that it has actually been pushed along. It has been combined with special relativity to become quantum field theory and so on. It's proving much harder to do that with Bohmian mechanics. So there are other issues that happen with these different interpretations that can lead to people believing in them or not believing in them. But right now, I don't want to call it a matter of faith. I mean, there is solid mathematics in all of these things, but they're not empirically distinguishable, except for collapse theories. Collapse theories do make a prediction. They predict where the quantum classical divide lies. So the collapse theories basically point out that if the mass of the system that you're looking at gets beyond a certain point, it will spontaneously collapse within a certain time frame. And so now you can imagine doing the double slit experiment with larger and larger entities. So starting with electrons, you can then go to atoms, molecules, to see if you get the interference pattern, right? And the moment the interference pattern disappears, it means that the quantum object that you're sending through the double slit has collapsed to in such a way that it's only going through one or the other, and it's not interfering anymore. So those experiments are being done. They have actually managed to send C60 molecules, 60 carbon atoms, through this double slit. It interferes. The largest molecule that has been sent so far through a double slit has, I think, 800 atoms or 10,000 atomic mass units. These are massive molecules, and they will go through the double slit and interfere. They behave as if they're going through both. So the quantum classical boundary has not yet been seen. But collapse theories do make predictions that are not quite within reach of experiments, but maybe in another 5-10 years.
Thank you.
We should take further questions after giving people a chance to leave. There are copies of the book available if you would like to pick one up on the way out.
Thank you very much.
Thank you.
Thank you.